I would like to begin my talk on adsorbate-adsorbent interaction potentials by paying my tribute to Douglas Morris Ruthven, who was born in 1938 in Ernakulam in India, and he died in 2021. I've learned a lot from Ruthven's textbook, Principles of Adsorption and Adsorption Processes. Indeed, the material I will present today is largely contained in chapter 2 of the textbook, which was published in 1984. The choice of the right adsorbent for a given separation task requires deep understanding of the various factors that contribute to the adsorbate-adsorbent interaction potentials. If we ignore pi complexation and chemical bonding, the major contributions to the adsorbate-adsorbent interaction potentials are the London-van der Waals interactions and the electrostatic interactions. The background information and details are provided in the supporting information to my paper published in ACS Omega in 2022. Watch also the video presentation, Adsorption versus Diffusion in Fungicide Zeolite on my YouTube channel. The London-van der Waals interactions consist of the sum of the attraction and repulsion forces that are usually expressed in this form, where R is the distance between the adsorbate and adsorbent. The forces of attraction and repulsion are proportional to the polarizabilities alpha of both these adsorbate and adsorbent atoms on the surface, and the polarizability increase with the size of the molecules. The expression for A and B are provided here, where C is the speed of light, Chi is the magnetic susceptibility. It is very common to write the London-van der Waals interaction in terms of Lennard-Jones 612 potential. It is interesting to note that despite what the name London might suggest, Fritz Wolfgang London was actually a German. Johannes Diederik van der Waals won the Nobel Prize in 1910, and he was a professor at the University of Amsterdam, where I am also located. The separation of noble gases such as helium, neon, argon, krypton, and xenon are essentially based on the differences in the polarizability that are in turn related to the molecular weight or molar mass of the noble gases. The larger the gas molecule, the larger is the polarizability and the stronger is the adsorption strength. Watch also my presentation on separation of noble gases on my YouTube channel. The separation of hydrocarbons such as methane, ethane, propane, nominal alkanes are also based on the differences in the polarizabilities that are related to the molar masses of the adsorbates. Let us examine the key properties such as polarizability, dipole moment, and quadrupole moments of gas molecules such as carbon dioxide, methane, carbon monoxide, nitrogen, and oxygen. Here I plot the polarizability versus the quadrupole moment, and we note that the polarizability of methane is practically the same as that for carbon dioxide, but carbon dioxide has a significantly higher quadrupole moment. We also note that the quadrupole moment of nitrogen is about a factor 4 higher than that of oxygen. Of these gas molecules, only carbon monoxide has a dipole moment. For separating CO2 from methane, we can exploit the large difference in the quadrupole moments between CO2 and methane. Methane has a 0 quadrupole moment by electrostatic interactions with the extra framework cations. Similarly, the selective adsorption of nitrogen from mixtures with oxygen is achieved because of the large quadrupole moment of nitrogen that is 4 times larger than that of oxygen. For CO2 capture from flue gases, we rely on the large differences between the quadrupole moments of CO2 and nitrogen. And also the polarizability of CO2 is higher than that of nitrogen. Let us examine the electrostatic interactions between a gas molecule and the extra framework cation. That can be either lithium, sodium, potassium, magnesium, calcium, strontium, or barium. Also indicate here the size of the cation, the radius of the cation in angstrom values. That R represents the distance between the center of the gas molecule and the center of the cation. Basically, we can distinguish between 3 types of electrostatic interaction potentials. One due to induced dipoles. The second one due to the interaction of the electrical field with the permanent dipole of the guest molecule. And thirdly, we have the interaction of the electrical field gradient with the quadrupole moment of the gas molecule. Here Q represents the charges of the extra framework cation, and R is the distance from center to center between the guest and the cations. In all cases, we note that the potential energy of interaction is proportional to the charge, or the square of the charge, and inversely proportional to the distance to the power 2, distance to the power 3, and the center to center distance to the power 4. In other words, larger electrostatic interactions are achieved with smaller cations because the center-to-center distance is smaller if the radius of the extra framework cations is smaller. The electrostatic interactions increase with the valency of the extra framework cation. A bivalent barium cation would contribute to a greater extent to the electrostatic interactions. And larger dipole, larger quadrupole, higher polarizability will all lead to larger magnitudes of electrostatic potentials.